Now we have understood the principle behind potentiometer. Let us read or let us understand once again. The principle behind potentiometer is quite simple. That means potential drop remains constant throughout the whole length of the wire. That means phi is delta V upon delta L, that remains constant throughout the whole wire because wire is uniform. Wire is uniform. So the potential difference between A and any point L is simply, what is this? So as we have seen that potential difference between A, this starting point, 0 or positive point, this positive point, and any length L. So what would be that? That potential difference is this epsilon L. Epsilon is again a potential, L is potential difference at point L, is simply potential gradient into length. Please remember, always check whether this potential gradient is given in per centimeter or per meter. Accordingly, if it is in per meter, then you use length in per meter. If it is given in per centimeter, then you use length in centimeter. So that is only thing you have to remind. But the principle is simple. Due to uniform cross section of wire or due to uniform wire, we have a potential gradient which is constant across the whole wire, or potential dropped at any part of this wire which has same length is equal. How? Let us say that this is 100 centimeter piece of wire. So this is 10 centimeter here. So this is 0 centimeter, this is 100, this is 10, this is 20, this is 70, and this is 80. Okay. So if we connect this to a battery of, let us say, 10 volt. So what would be the, remember here I have taken a wire of 100 centimeter only. So we have taken this wire. So this is 0, this is 100 centimeter. So what would be the potential gradient? Phi would be 10 volt. That means total potential difference upon total length. So 10 upon 100. So 0.1 volt per centimeter. That is the potential gradient. Now potential difference at 10 to 20 would simply be, what would be the potential difference from A, this starting point, this is 10 centimeter, this is 20 centimeter. So 5 at 10, sorry, this at 10, potential gradient or potential difference at 10 is 5, which is 0.1 volt per centimeter, into this 10, simply 1 volt. So if it is 10 volt, it is at positive 10 volt. So this would be at 9 volt only. This would be at 9 volt. Now at 20, what would be there? So at 9, at this 20 would be 5 into 20. That means potential drop would be 2 volt. So this is at 1 volt, this is at 2 volt. So see, the distance is 10 centimeter, voltage drop or potential drop is 1 volt, this is 2, this is 1. So at every 10 centimeter, voltage drop is 1 volt. Similarly, you can see, check here. So at 70 and 80, so potential, let me remove this thing. Potential at 70 is equal to 5.1 into 70, that means 7 volt, 7 volt, this is 7 volt. And potential at 80, 5 into 80, that means 8 volt. So this is again, this is 10 centimeter, potential drop is again 1 volt. So you can see whether you take position or the points anywhere, if their length is same, potential drop is also same. At every 10 meter, potential drop is 1 volt for this special case. For different cases, potential drop could be different, but the working principle of potentiometer is that potential drop at any given length is constant. Now let us see this figure. So now we have understood potential drop at any point which is at L distance from A. So that point is some distance, that distance is L from A. So potential drop or potential difference is simply potential gradient into length of that, where phi is the potential drop per unit length, or it is called potential gradient. So potential gradient is simply potential drop, that means delta V upon delta L. So that is potential drop, potential gradient phi. Now let us see this first figure. This shows first application of the potentiometer, and that application is comparison of EMF of two cells, epsilon 1 and epsilon 2. So these cells have two EMFs. First cell have epsilon 1 and second cell has epsilon 2. We have to compare the EMF of these two cells. Now let us see. So we have this primary circuit which is powering this potentiometer. So this is our primary circuit. In this primary circuit we add these two cells, cell epsilon 1 and cell epsilon 2, which has EMF, which are EMFs of these cell epsilon 1 and epsilon 2. Now we have a galvanometer. Remember, if you see the diagram, this side of battery is positive, the side of cell is connected at this point is also positive. So you can see that the battery and this side are both positive. Okay, so we connected these cells at point A as well. Both the cells are connected with positive terminal at A. Now these cells are connected with a two-way key to a galvanometer. So here we have a galvanometer connected, and one end of the galvanometer is connected to jockey. Jockey is nothing, jockey is a pen-like structure which can move freely on the whole wire. Jockey is nothing but a pen-like structure which can move freely on the whole length of wire. So first let us understand what does this two-way key do. So two-way key, so if we want current or if we want this first cell to be connected, so what would we do? We insert a key between 1 and 3. So what will happen? This circuit will become complete. This for cell 1. If we want current to be flown or circuit 2 to be completed, what would we do? We simply add a key between 2 and 3. So this is a two-way key look like. So we have a key, we have this kind of structure. So we have two-way key. So in two-way key, if we insert the key here in first place in gap 1, that means this first and second is common, or third we can call it 3 and 1. So first is connected with 3 and circuit is complete. If we remove key from this first one, we put key into this gap 2, then first is removed, 3 and 2 are connected. So this is called two-way key. Similar to one-way key, there are two gaps. So any of the one gap is connected at a time. So either we can connect 1 and 3 or we can connect 2 and 3. 3 is common, 1 and 2 can be changed if we want to use first cell or we want to use second cell.